All right, this lecture is on correlation, and this is the second lecture in the series about correlation. So recall from the previous lecture that a correlation describes a relationship between two variables. Um, we could be a little bit more precise and say that a correlation measures the relationship between two equal interval numeric variables. So it is possible to, at least the correlation that we're going to review in this class, which is the Pearson product moment, it is possible to calculate measures of association between variables that are measured using different scales of measurement. But what we're talking about here is a measure of the relationship between two variables when those variables are numeric, okay, that is, their values are numbers, and when there is an assumption that the values are separated by an equal interval, such that the difference between a 1 and a 2 is the same as the difference between a 3 and a 4. Okay, so that's just a little bit more clarification. And then some of the examples that I gave last time is that just some practical things that we might be interested in determining whether there's a relationship between, we might say, is there a correlation between high school grades and college grades? Is there a correlation between an employee's motivation and their job performance? And is there a correlation between an employee's job satisfaction and their intention to quit the job? And in the first two examples, we would have correlations that we would probably predict would be positive. That is, the higher the grades you get in high school, the higher the college grades you should get. And similarly, the lower the grades that you got in high school, probably the lower college grades that you'll get. Same thing, employees that are motivated ought to be better performers, and those that are less motivated ought to be less good at their job. But here, so positive relationships in the first two cases. In the third case, this would appear to be a negative relationship. That is, the higher the job satisfaction, the lower one's intentions to quit. So with a negative correlation, we've got high scores on one variable going with lower scores on the other variable. So in the previous lecture, I reviewed how to graphically describe correlations using a scatter plot. That there's different types of correlations. I just reviewed a positive and a negative correlation, but we could have a zero correlation. We can also have a curvilinear correlation. We reviewed how to calculate a correlation coefficient, so I'll go over that again. The new stuff for this lecture is determining the statistical significance of a correlation. So a correlation coefficient is both a descriptive statistic in that it describes the relationship between two variables in a set of data, but we can also use it as an inferential statistic. That is, we can take a sample of data, determine the association or a correlation between two of the variables in our data, and then use that to infer whether there is a relationship between those two variables in a broader, larger population. So we'll go over the statistical test of the correlation, talk about some issues related to interpreting correlation coefficients, and then review correlation as a measure of effect size. So let's again go over how to calculate a correlation. And I've got an interesting set of data here. So we've got 6 different participants, and they were asked, how many hours of leisure do you engage in a week? And then what is your typical mood over the week? Okay, so we might have a hypothesis that, the more leisure you have, the better mood one will be in. Well, let's take a look at, we can get a sense of this relationship when we create a scatter plot. Recall that to create a scatter plot, we create 2 axes, a horizontal axis and a vertical axis. We put a variable on the horizontal axis that we think should be the predictor variable, and we put the outcome variable on the y-axis. So here, even though I'm going to discuss later in the lecture that it's a well-known phrase is that correlation does not equal causation, because we could see a relationship between two variables and that doesn't necessarily establish which one is the cause of the other. We often just have our own theories in our mind about which variable is likely to come first and be the cause of the other. So it makes sense that in this case, we're going to suggest that hours of leisure would predict the mood that one is in. Anyway, what we see here is that we clearly have a curvilinear pattern. Okay, we've got this inverted U-shaped pattern that is happening. So it looks like there's kind of this optimal number of hours of leisure where people are reporting the highest moods. Okay, not enough leisure, poor mood, but too much leisure, also poor mood. Okay, and so that's an interesting finding, and again, that actually corresponds with research on TV watching, is that people tend to have the most enjoyment or feel the most relaxed when they watch a moderate amount of TV. If you don't watch, say, enough TV, whatever that is, and everybody's different, but we're talking about on average, hey, that could be because you're super busy with work or with school, and you're like, oh, I haven't even been able to watch just even 1 hour of my favorite program this week because I'm so busy. Alternatively, people that spend all of their time watching TV, maybe they're not engaging in exercise or social relationship or something like that. So they're in a poor mood for those reasons. Anyway, that's the pattern of data that we found. Recall that the correlation coefficient is a measure of the linear association between two variables. So it'll be instructive to see what happens when we try to calculate a correlation coefficient when we clearly have a pattern of data here, but it is it's a non-linear pattern. Okay, so here we go. What I like to do in calculating the correlation coefficient is create, when I'm doing these hand calculations, all the steps, is I like to create a table so I can see all of the steps in the process. And so this is in the previous lecture. This is how I introduced how to use the correlation formula to calculate a correlation. So you notice that I've got the X variable hours of leisure, I've got the Y variable mood, and then I've created all these columns of data. Ultimately, what we want to do to calculate a correlation coefficient is come up with our cross product of our Z-scores and our Y-scores. The correlation coefficient is really just the average of the cross products of the Z-scores. So we're going to get the cross products, we're going to sum those up, and then divide by the number of scores, which is 6. But in order to do that, working backwards, I need to transform my X scores into Z scores and my Y scores into Z scores. Okay, so I'm not going to show every single step, but the first thing that we would do is transform our X scores into Z scores. So these are our hours of leisure, and we're just going to express hours of leisure as a Z score. Okay, so the average here, the mean, was 6.5 hours of leisure, and then for each of our people in our data set, we can express their score as a Z score, right? So this person that engaged in 10 hours of leisure, they have a Z score of 1.58. That means that 10 is 1.58 standard deviations above the mean. Going to do the same thing for the Y scores. So this is mood. Again, it's just calculating the mean. Once we have the mean, we can figure out the variance and the standard deviation, and then the Z-score is nothing more than the deviation from the mean divided by the standard deviation. So again, just to interpret, this person that has a mood of 3 scores 1.08 standard deviations below the mean of 6. We calculate our cross products by just taking, by multiplying a person's Z-score on X by their Z-score on Y. So we're just going to take negative 0.68 times 0.36. That's going to give us a cross product of negative 0.24. It's kind of instructive to just take a look at this cross product and say, okay, I've got a negative cross product. Would that contribute to a positive correlation or a negative correlation? Recall that on balance, when the cross products are negative, that's going to contribute to a negative correlation. And that kind of makes sense because we've got a low value being paired on X being paired with a high value on Y. And so when low scores are paired with high scores, that's a negative correlation. All right. So we've got our cross products, and we'll notice that some are negative and some are positive, and they're of varying sizes and magnitudes. When we sum up those cross products, we get a sum of cross products of 0.49, and then we're going to divide this 0.49 by the number of scores, number of pairs of scores, which is 1, 2, 3, 4, 5, 6. And when we do that, we get an R of 0.08. So what does that mean? It means we have a close to zero correlation between hours of leisure and mood. Okay, so this is an illustration to show that really our correlation coefficient in this formula is meant to capture the strength of a linear association, that is a straight line relationship. We clearly have a strong relationship in these data between hours of leisure and mood, but that won't be captured if we try to calculate a Pearson's correlation coefficient, because the Pearson correlation is an index of linear relationship, not curvilinear relationship. Just to further emphasize why that's the case. Taking our cross products, these z-scores, are meant to capture whether our data primarily fall in a pattern such that we've got positive cross products in this quadrant and this quadrant, or negative cross products in this quadrant and this quadrant. Okay, so that when this is from the previous lecture, when our data will fall primarily in these two quadrants, we're going to get positive cross products, so that when we sum those cross products up, we're going to get a positive number for our correlation. Alternatively, when our data primarily fall in these two quadrants, we're going to get negative cross products and negative cross products, and when we sum those up, we're going to get a negative number, so that will result in a negative correlation. As you can see with the curvilinear pattern, what I've done is I've just taken the cross product from the table on the previous slide, and I've just listed the cross product by each of the data point. So you can see that we've got a combination of both positive cross products and negative cross products. Therefore, when we sum them up, we get close to a zero correlation, and that is really, kind of definitional to what it means to have a zero correlation, is that we've got cross products between our z-scores, which are both positive and negative, so that it doesn't result in a positive pattern, it doesn't result in a negative pattern. There's supposed to be no pattern at all, okay? But you can see this kind of ironic thing that happens when you've got a strong curvilinear relationship, is you can get what appears to be the zero correlation as well. So when you're reading research reports and a researcher reports a very low correlation, and you think to yourself, gosh, I could have sworn that there would have been a relationship between those two variables, maybe it's a curvilinear pattern. Maybe they tried to investigate to see whether there would be a positive correlation, but it's actually a curvilinear correlation. Sometimes there's too much of a good thing, right? So that at first you have a linear relationship, but then there's too much of a good thing, and then that pattern drops off. So a too much of a good thing effect, and these are actually documented in psychological research, it results in curvilinear patterns, and you'd not see a strong correlation if there's in the event that there's a curvilinear pattern. All right. So that was meant to, one, illustrate that the correlation coefficient is an indicator of straight line or linear relationship between two data, and just some extra kind of practice or overview with how it's calculated. Let's move on to review the statistical significance of a correlation coefficient. I had mentioned that a correlation is a measure. It can be used as a descriptive statistic, much like a mean, much like a standard deviation, to kind of merely describe the relationship, the strength of the relationship between two variables. However, in addition to being able to describe the direction as well as the strength of the relationship, we may also want to test whether that correlation is statistically significant. In the case of a correlation, the question is usually whether the correlation is statistically significantly different from zero. Okay. So that is, the null hypothesis in this case is usually that in the population, the true relationship between two variables is no correlation. Okay? That's the null hypothesis, Recall that the null is always that there's no effect. All right, so let's just say, and this we'll kind of do a working backwards. We'll do an example where we start with all of our steps of hypothesis testing, but we'll just do a working backwards. Like we'll start with our data, and let's just say that we jumped straight to calculating our correlation. Okay, so in this example, I've changed the data, and we've got hours of leisure and mood. So it's the same example, just different data. Here, what we see in this sample of 6 participants that we collected, we calculate that the correlation between leisure and mood among these 6 participants that answered our survey is 0.51. And so the question is that a statistically significant value? That is, would we be able to reject the null hypothesis that in the population, these variables are correlated at 0? Okay, so what do we need to do? And this is just a scatter plot of our data to get a better sense of that positive relationship. Again, asking the question, is this correlation of 0.51 that is based on 6 participants statistically significant? Like our other tests, like our other statistical tests, in order to determine whether a statistic is statistically significant or not, we need to kind of have this thought exercise and ask what happens if we assume first that the null hypothesis is true. So when it comes to testing correlation, our starting place is the null hypothesis, and that the true population, the true correlation between these 2 variables in the population is 0. Here's what that scatter plot would look like. Okay, and again, you could say that that's a totally artificial hypothesis. Like that seems wrong to me, but that's the way that statistics are done. You start with the null. That's always the starting place. Okay, so we'll start with the null hypothesis that there's 0 correlation. There's no relationship. Okay, what does no relationship mean? It means that high values go with high values as well as low values. Okay, that and you could have a lot of leisure and either be happy mood or in the middle or not a happy mood. You could have very low levels of leisure, and same thing, good mood, moderate mood. Okay, so 0 correlation. So that's our starting place under the null. And then what we're going to try to test is what is the probability that in a sample of 6 people we would get a correlation as strong as 0.51 if this is really true. Like, what is the likelihood that we would sample from 6 people a correlation as strong as 0.51 if the null is actually true? That's the logic of the null hypothesis significance testing when it comes to correlation. Okay. So in doing this null hypothesis significance testing with a correlation very similar to our other statistics, like a t-statistic, like an F ratio, we end up with a sampling distribution. And this is the thought exercise. What happens if we repeatedly sample from a population in which the true correlation is 0? Okay? The result is that we end up with a sampling distribution of correlations. Okay, so we can think about just doing kind of the little study where we've got this population of people, the true correlation is 0. I'm going to randomly grab 6 people, ask what their number of hours of leisure is, ask what their mood is, calculate the correlation, and then put it in a pile. And then I'm going to do that again. I'm going to randomly sample 6 people, find out what their hours of leisure is, find out what their mood is, calculate the correlation between the 2, and put it in the pile. And I'm going to do this over and over and over and over and over and over and over again. Okay? What do we expect to happen? Well, over the long run, if the true population correlation is 0, we expect that most of those sample correlations that we calculate are also 0. Some might be a little higher, some might be positive, some might be a little bit lower, some might be a negative correlation. A very, 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 very small number of those correlations would be a perfect positive 1. Okay? Highly improbable, but it could happen. a very, 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 very small number of those correlations would be a perfect negative one. Okay, highly, highly unlikely, but it could happen. Okay, so this is basically the range of what is possible. Okay, but we can quantify that a little bit better. It turns out that the sampling distribution of the correlation coefficient follows a t-distribution. So we've already learned about t-distributions in this class. Okay, a t-distribution is going to be centered around a value of 0. Okay, and under the null hypothesis, that would mean that the most typical average value of all of these possible samples that we could take would be 0. The exact shape of the t-distribution depends on the sample size, and more precisely on degrees of freedom. So recall that there is actually a family of t-distributions, and each one has its own shape based on degrees of freedom. The larger the sample size, and therefore the higher the degrees of freedom, the closer the shape of the t-distribution to a normal distribution. The smaller the sample size, and therefore the smaller the degrees of freedom, our t-distributions are wider with thicker tails. Okay, so it just represents kind of what is more versus less likely in terms of a sampling process. Okay, so there's many different t-distributions, and there will be a unique t-distribution based on degrees of freedom. For a correlation, degrees of freedom is determined by taking your sample size minus 2. In this particular example, we had 6 participants. 6 minus 2 is 4. So our sampling distribution of our correlation coefficient is a t-distribution with 4 degrees of freedom. What we're ultimately going to do is say, when the correlation that we calculated, in this case 0.51, is converted to a t-score, what is the probability of that particular t-score in a distribution with degrees of freedom of 4? Okay. What we can do is the same thing with doing our t-test, is ahead of time, we can set a critical value. We can set a critical value associated with an alpha level. By convention, we use alpha 0.05, corresponding to a probability of less than 5% that we would get a sample statistic this large if the null hypothesis is true. Okay, so that critical value will correspond to a t-score. So it's a very similar process. What we're going to do is just convert our r to a t and then determine whether that t surpasses a critical value or not. So it's really the same procedure as we're used to with the t-test. Turns out that the formula to convert a correlation coefficient to a t is this. It's a little bit nasty. It's not very intuitive, but we can say this. The denominator, in other words, the bottom, represents the standard error. So in other words, how much can we expect a correlation to differ from 0 just by chance alone? Okay, just by random sampling error. So we're ultimately expressing our t as a standard error, which is the exact same interpretation that we've had this whole time for what a t-statistic represents. It represents the number of standard errors away from the mean. Okay, so what we're saying is, under the null hypothesis, we expect that our most of our samples should be 0 under the null hypothesis, and on average over the long run, they would be. Okay, our sampling distribution would be centered around an average of 0. We're going to say how many standard deviations away is a particular sample that correlation that we just calculated, and if it is a sufficient number of standard errors away, we'll reject the null hypothesis. Okay. One thing that I'll point out is that this part of the denominator, this n-2, reflects degrees of freedom. Again, degrees of freedom are calculated as n-2, and that's because there's 1 degree of freedom for each variable. So we had 6 participants, minus 2 is 4. We'll be able to see the influence on sample size and degrees of freedom later in this lecture in terms of how that affects the standard error and therefore the size of the t. All right, so let's just go through. So there we go, degrees of freedom. Um, let's kind of start now. Let's go back to the beginning and just start with our more traditional steps of hypothesis testing. So step one is to state the null and the alternative hypothesis. Null hypothesis, being a little bit sloppy here because the null is not the exact opposite of the alternative, but we'll just go with it. Null hypothesis would be that the true population correlation is 0. And let's just say that we're going to have a one-tail test in this case, that we're going to make a directional hypothesis, and we are going to predict that no, actually the true population correlation is greater than 0. Okay? Just like before, it's possible to have directional and non-directional hypotheses to perform a one-tail versus a two-tail test. Here we've got a directional hypothesis because we're predicting a direction of the relationship. We could, if we wanted, have a non-directional hypothesis test and just make the prediction that we believe that there's an association between these variables, and that association will be different than 0. But we aren't predicting whether there will be a positive correlation or a negative correlation. We're just going to see, is that correlation significantly different than 0? Most of the time, when researchers and statisticians have hypotheses about correlations, most of the time it's directional. Most of the time there's some prediction about the direction of the relationship. All right, so that's step one. Step 2 and step 3, we specify what the comparison distribution looks like and what the cutoff value should be. Our comparison distribution is a t-distribution with n-2 degrees of freedom. That will always be the case when doing statistical tests for a correlation coefficient. So now we just need to determine the cutoff value at which the null hypothesis should be rejected. Good thing we can use the table of cutoff scores for the t-distribution, which we're already familiar with using. We're going to use degrees of freedom 4, and we're going to do a one-tail test, and we're going to use our alpha at 0.05. Okay, so that gives us a critical t-value of 2.132. So when we convert our correlation of 0.51 into a t, we're going to be looking to see whether that t that we converted our correlation into exceeds in the positive direction, whether it exceeds a critical value of 2.132. All right, here's a formula. Again, this would not be something that I would expect people to commit to memory. This is something that you can look up. If you ever have to do a hand calculation, really for the most part, people are going to do statistical tests using computer software, but this just gives you an appreciation for where the numbers come from. So really, it's just a matter of plugging in numbers. We've got our correlation. We've got 1 minus the correlation squared. We've got degrees of freedom as this quantity. So it's an involved formula, but it's really just plugging in numbers, and I know you all can do that. So when we work through the numbers, we get the first value 0.74 divided by degrees of freedom, which is 4. So we're going to divide 0.74 by 4 and then take the square root. What that gives us is 0.43. And again, that can be interpreted as a standard error. So what that says is, based on a sample of 6 people, we would expect that an average amount of error is 0.43. Okay, so it would be typical and not surprising to get correlations that are in the range of 0.43 to like negative 0.43. There'd be a lot of correlations that we could sample that would be in that range, and that's fairly probabilistic. Like that's not too unusual. Okay, so that's what that number means. Like that's a standard error. So then what we're doing is we're saying, okay, so how many standard errors is 0.51 away from the mean? So when converted to a t, 0.51 is 1.19 standard errors away from the mean, okay, in that particular t distribution, which is based on degrees of freedom 4. Okay, Does that surpass the critical value? No, it does not, because we had set up as our critical value 2.132. That is, whatever correlation we would need needs to be 2.132 standard errors away from the mean of 0, because those correlations happen less than 5% of the time if the null is true. So what we're getting here is a result that we can say happens more than 5% of the time if the null is true. Okay, so we are going to fail to reject the null hypothesis. What does it mean in practical terms? Based on our data, we don't have sufficient evidence to conclude that there's a positive relationship between hours of leisure and mood. So we'll fail to reject the null hypothesis. And to be really precise, we had set up the null, or I had set up the null hypothesis as rho. Okay, that's the Greek symbol rho for that squiggly p. It's the symbol for the population correlation. Not to be confused with p like probability, but it's a Greek symbol that looks like a p rho. We had set up that rho was equal to 0. We should have set up as a null hypothesis, because we had a directional test, that rho is less than or equal to 0. Okay? Because what we're concluding here is that we don't have sufficient evidence to conclude that there is a positive relationship between hours of leisure and mood. So we have to accept the null, fail to reject the null, accept it for the time being, that rho is less than or equal to 0. But of course we had a small sample size, right? And so it's worth asking, like, well, what would happen if we calculated a correlation that was that big, 0.51, but we had done so using a larger sample? In this case, a sample of 52. And that 52 seems a little bit random, but I used that so that we could have degrees of freedom that was a nice even number for our lookup table. So I kind of tweaked the example. All right. So what if we have a larger sample? Well, let's just take that same correlation. Okay, we're going to imagine that we found a correlation of 0.51, but in this case, using a sample of 52 people. The formula is the same. The only thing that is going to differ, and you can toggle back to the previous slides. You can look at the previous slides. The only thing that is changing here is degrees of freedom that used to be 4 and is now 50. You can see the influence on the standard error. Okay, that when we divide 0.74 by 50 and then take the square root, we get a standard error of 0.12. So what that means is that when we have a sampling process that is based on a sample of 52, we expect there to be much less error in the process, much less standard error. Okay, one standard error is only 0.12. So in that case, it wouldn't be unusual, even if the true population correlation is 0, to get correlations that are like 0.12 to negative 0.12. Like that would be a range that would be pretty typical. But once we start getting correlations that are bigger, and we need to specify how much bigger, but certainly like two standard errors ends up being kind of like, kind of like a rule of thumb to say like, oh, that sample statistic is 2 standard errors away from the mean of 0, the null hypothesis. That's getting big. Turns out when we convert 0.51 to a t, 0.51 is 4.25 standard errors away from the mean of 0. So we should have in our brains like, well, that's pretty unusual. That doesn't happen much of the time. Okay. Now the other thing that we need to adjust, of course, is the critical value. And so based on degrees of freedom of 50, the critical value is also less. So you can see the difference between the two calculations and the two kind of research studies, if you will. Based on the exact same correlation, if that correlation is only based on 6 people, so 4 degrees of freedom, we're going to get a non-significant result. However, by just having more people in the study, we end up with a statistically significant result. And hopefully, intuitively, that makes a bit of sense. Essentially, what we're saying is, based on only 6 people, that 0.51 could just be randomness. Okay? In other words, it really could be the case that the true population correlation is 0. There's no relationship at all between hours of leisure and mood. And we just happened, this one time we did the study, we just happened to get a correlation of 0.51 based on these 6 people. And that could just be sampling error. That could just be we got to these 6 random people and they're just, it's a random sample, there's sampling error. Okay? But if it's based on a sample of size 52, now it is statistically significant because we're saying, oh, it's quite unlikely that if the null hypothesis is true and if the true population correlation is 0, it's actually quite unlikely that we would get a correlation that big. So that's the difference. And it really just has to do with what is the likelihood that the sample statistic that we calculated could just happen due to sampling error, just due to chance, randomness. And in this case, that's likely, and in this case, it's not. Okay, and then again, that changes the inference because this 0.51 could happen due to randomness. We're like, well, true population could be 0. I can't rule that out. But in this case, we have to say, nope, I would reject the null hypothesis. I really don't think that the true population could be 0 because if it was 0, we wouldn't get a number this big based on 52 people. All right, so this is emphasized in this table in the chapter. What this table shows you is the approximate number of participants in a research study needed for 80% power using a correlation for testing a hypothesis at the 0.05 level. Recall that power is a researcher's ability or a statistical test's ability to reject the null hypothesis and to find a significant result. Okay, so really to detect a true effect when a true effect is there. So what this shows is that when there's a very small correlation, you need quite a few participants in the study to say that's a real effect, it's not due to randomness. Okay? As the size of the correlation goes up, as the effect size increases, we need smaller and smaller studies in order to be able to have a statistically significant result. And it's based on the same principle that I reviewed by going over, calculating the statistical significance of a correlation based on 6 people versus 52 people. When a correlation is small, we need a lot of people to say, yeah, it's small, but it's not due to chance. There must actually be a true correlation in the population because even though the correlation that we calculated in our sample is small, we would not get a small correlation based on this number of people if a true correlation didn't exist. But the fewer people, the larger the correlation needs to be in order to conclude that the correlation that you calculated is not due to randomness and it's not due to sampling error. So in this case, we'd say, yeah, sure, there's only 22 or in the case of a one-tail or 28 in the case of a two-tail test. But despite what would appear to be, small sample size, if we calculate a very large correlation, we can conclude, hey, that's not due to randomness. Or it's unlikely due to randomness if the null hypothesis is true. Like we just wouldn't get a correlation that large. Even with only 28 or 22 people, you just are unlikely to get a correlation that large if the true population correlation is 0. Okay, so study this. This is kind of important in terms of the concepts really for the whole class because it illustrates the basic principle that the larger the effect size, the smaller the sample you need to be able to detect statistical significance. You'll also see one of the influences that we've previously talked about on power is that you will have a more powerful test when you use a one-tail versus a two-tail test. Okay, and just a further illustration to try to drive home this point. It's possible to have other lookup tables of statistical significance of critical values and rather to be the t-values. Some statisticians have said, you know what, rather than having to convert to a t-value, just tell me what correlation I need. Okay, and so this is what we see. And so this is an example of a lookup table of critical values. And so I'm just going to use, we did just to keep it consistent with the previous example, we've got a one-tail test, alpha level 0.05. Here's our degrees of freedom 4. Degrees of freedom 50 were not in this particular table. They start skipping, but I'll just give you, examples with 40 and 60 degrees of freedom. So it's based on the same principle. Based on a small sample size, you need a much larger correlation to be able to conclude that that correlation is statistically significant, that is, unlikely to have been sampled from a population with a true correlation of 0. So in this case, we need a correlation that is bigger than 0.729. Okay, so in other words, a correlation of 0.73 would do it. So if we only have 6 people in our study and we want to try to establish that there is a relationship between 2 variables in our study, hours of leisure and mood, for example, we are going to need to calculate a correlation that is at least 0.73 to be able to conclude that there is a statistically significant result and therefore a true relationship. There's likely a true relationship in the population. Okay. Notice that there's only positive values here. It's because of the symmetry in the t-table or the symmetry in the sampling distribution is that this corresponds to a correlation of 0.729 or negative 0.729. Okay, here, when we've got a larger sample size, we need a much smaller correlation to be able to conclude that it is statistically significant. Okay, so even a small effect, and here, even when we go to degrees of freedom that are very, 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 very high, we can even see that the size of the correlation goes down. So in even small effects, even small effects can be determined to be statistically significant to the extent that the sample size is large enough. All right, so that was statistical significance. So let's talk about a couple other issues or considerations. So one is causality. And there's 3 possibilities when we calculate a correlation, we see that there's a relationship. Let's even say that there is a statistically significant relationship. There's 3 possibilities. One is that our x variable can cause our y variable. Our second possibility is that our y variable can cause our x variable. And then the third one would be that there's some third factor that are the cause of both x and y. So going back to our example. Actually, this was from a previous lecture because we had hours of leisure and mood. You might recall from a previous lecture, one of the examples we were talking about was exciting activities and marital satisfaction. So here's our x variable and here's our y variable. So it could be the case. So when we collect some data, we calculate a correlation coefficient, we see that there is a relationship, let's just say that there is a positive relationship between exciting activities and marital satisfaction. One possibility is that X causes Y. To the extent that a couple engages in exciting activities, they feel more marital satisfaction. It could go in that direction. Alternatively, it could be that Y causes X. So to the extent that a couple is happy in their marriage, they go out and they do fun things together. To the extent that they're not very happy in their marriage, they might be avoiding each other, or they might be, who knows, having an affair. We don't know. But there's less exciting activities, and it's because marital satisfaction is either high or low. Okay, so we're happy with each other, we go out and do stuff. We're not happy with each other, we avoid each other. Okay, it could be the case that there's the third option is that there is some third variable that is the cause of both. So it could be the case that both spouses, both partners in the relationship are experiencing a low amount of work stress, and they're like, yeah, my marriage is great right now because I'm able to spend more time and we enjoy each other more and we have conversations and I'm not thinking about work all the time, so my marriage is just better. And it's also a byproduct of having this lower work stress that there's time to engage in exciting activities. Okay, change this to high work stress, and it's like, oh, my marriage sucks right now because I'm thinking about work all the time, and I'm grumpy, and I'm cranky, and I'm not having good conversations, and I just don't take the time, and we also don't take the time to go do the fun things that we used to do anymore. Okay, so a correlation between two variables cannot determine whether X causes Y, whether Y causes X, or whether some third variable is the cause of both. Only the research design can determine a causal relationship. So when we do a survey, when you just throw out a questionnaire, it's like an online questionnaire, and say, hey, fill out my questionnaire. We might have in our mind some theory that it's exciting activities that causes marital satisfaction. But that particular research design is not sufficient for establishing causality. What would you need? Well, it's really a subject for a different class, like a research methods class, but you need another research design that establishes causation by establishing, one way to do that would be to say, we're going to establish which comes first. So for instance, let's see how many exciting activities people are doing in week 1, and then in week 2, we're going to measure marital satisfaction. We are going to then also rule out a bunch of other stuff. So we're going to rule out work stress. We're going to rule out whether they have kids or not. So we're going to take all of these other competing alternative explanations and we're going to rule those out. And so that can be done by the type of research design that you have, by measuring other variables. It's a question for a research methods class. But the point that I want to make sure to convey is simply observing a correlation between two variables tells you nothing about which is the cause of the other. Most of the time, anyway. All right, next topic that I want to review is the concept of proportionate reduction in error. So a correlation coefficient tells us the direction and the strength of a linear relationship. Bigger, larger correlations, that is, further from a mean of 0 under the null hypothesis, really, or just further from 0, mean a higher degree of correlation. Okay, so we can say that a correlation of 0.6 is larger than a correlation of 0.3. Great. To compare correlations to each other, most researchers often square the correlations. That is, they use R squared instead of R. And the interpretation of R squared is that it represents the proportionate reduction in error in predicting one variable from another versus using simply the mean. This is a concept that I will review in depth in further lectures. For the time being, it suffices to say that R could be used as a measure of effect size. R squared can also be used as a measure of effect size. R squared ends up being preferable in for some reasons, because what an R squared, in this case, a correlation of 0.3 yields an R squared of 0.09, and a correlation of 0.6 is equivalent to an R squared of 0.36, and we're able to make statements along the lines of R squared of 0.36 is 4 times as big as an R squared of 0.09. We're also able to make conclusions along the lines of knowing something about how much leisure somebody engages in explains 9% of the variance in their mood. Okay, and so that's a concept that we'll come back to. Okay, another issue that is worth talking about is something called restriction of range. With a restriction of range, you would figure out a correlation, but only in a limited range of possible values on one of the variables. And the issue with this is it typically results in an attenuation, in other words, reduction of the size of the correlation. So let's take this example. On the left side of this figure, we've got applicants for a job, and a particular company has created a test of job knowledge as a way to be used as a screener or for a way to select their employees. And what you would hope is that, or what you would see really, is that if you hired every single person, okay, if a company was able to hire every single person that took the test and then get a measure of their job success, okay, what they would find is that there'd be a positive correlation such that people that didn't do very good on the test weren't very good on the job, and that people that scored higher on the test were much better on the job. And then, of course, middle values goes with middle values. So there's this nice, pretty clear, positive correlation between scores on the test and job success. What often happens is we end up with an attenuation effect. And this is due to a restriction of range on the, we could say really on the test score variable, because we're going to limit our sample of people to those that got it, we could say, a good enough score on the test. Makes sense for in the real world. For practical purposes, you want to hire people that do well enough on your test of job knowledge. You don't want to hire people that don't know anything about the job. So good for the company, what that results in is mostly people that do well on the test, and then they're good performers on the job. We don't have all the people over here that wouldn't be good on the job. That's great. But what does that tell us about the validity or the accuracy of our test? If we calculate the correlation among these data, we get a weaker correlation than in this particular case. Okay? You can just kind of visually see which pattern seems to reflect a stronger positive correlation, this pattern or this pattern. Okay, if we zoom in, we've just kind of got this cloud of dots with, and if we do our grid here, we see that we've got highs going with highs, lows going with lows, but also some, just in this case, we've got some lows going with highs and highs going with lows. So we have a much smaller correlation here. And so if you're the HR person that designed the job knowledge test, and if you were asked as to substantiate the validity of the test, if you said, sure, yeah, I'll correlate test scores on my test with who ends up doing good on the job. Oh no, there's a correlation close to zero. I might have messed up. Well, no, didn't mess up. It's just that there's a restricted range. So what would you need? Couple things. There are some situations in which everybody is hired. That's a good way to validate it. Another thing that you could do is, this is getting into a research methods class, that's fine, but just in case you're curious, another thing that you could do is among the applicants, or to establish the validity of the test, have some outcome measure. Have some outcome measure that would be some indicator of job success. So in other words, among all applicants, give both measures. That would be something else it can do. Okay. It's also the case that, practically speaking, you often see a range in job performance among, current employees. So giving the test to people that are current employees is one way that people will often go through the process of validating a test or an instrument. But we should always be aware that if you're using current employees, you're likely to get a restricted range. Okay, so restriction of range. Here's another kind of practical example of that. Is that, let's just say we've got, in this example, school grade level, and this goes from the first grade to the 12th grade. So we've got high school students all the way to first graders. And then we have a test which is high school knowledge of geography. High school knowledge of geography. Well, do we think that a first, second, or third grader is going to perform very well on that test of geography? No, probably not. So in that case, school grade level is not at all correlated with knowledge of geography. That's because we have a restricted range. If we would have our full sample of data, and we've got first graders all the way through 12th graders, we would establish that there's absolutely a positive correlation between grade level and knowledge of geography, such that as we progress in school, we gradually know more, we gradually learn more, we gradually learn more, okay? So that, when we ultimately have a high school test of geography, we're seeing that people are gradually accumulating knowledge and doing better and better and better and better on that test of geography as they learn more in their schooling. But if we have a restricted range, it looks like there's no association at all between school grade level and knowledge of geography, when indeed we know that there really is. Okay, another issue is what to do when we have scores that are known as outliers. An outlier is a score with a very extreme value in relation to other scores in the distribution. And so by very extreme, it could be either very high or very low. Outliers can have an influence on the correlation coefficient, especially when we have small samples. So when there's only a couple data points, a single score that is an outlier can really affect the correlation. Sometimes the effect on the correlation can be that the outlier really reduces the size of the correlation. Let's look at this example. So here we've got an example of people are asked how many hours they slept last night, and then whether they're in a happy mood the next day. And for the most part, if you look at most of the data, we've got a positive relationship. And if we limited the data to these 6 data points, you would see that if you calculated this, there's a very strong positive correlation. But what happens when we have this outlier? The correlation is actually reduced, and it's turned into a negative correlation. Okay, and this would just happen that if we did our grids, you'd see that you've got this very large negative cross product up here that is contributing to the average of the cross product. So that outlier can have a very strong effect, in this case, reducing the size of the correlation. But it's important to know that sometimes an outlier can increase the size of the correlation. So let's just look at this example where we've got 1, 2, 3, 4, 5 students. Here's the original data. Here's the pattern. No correlation at all. But now here we add person F, who's an outlier. Okay. Now all of a sudden the correlation goes from negative 0.08 to positive 0.85. So the take home is that when we have a small sample size, or I would say especially when we have a small sample size, a single outlier can really affect the size of the correlation. Sometimes that outlier value can reduce the correlation. Sometimes it can increase it. And it really just depends on whether that outlier value, kind of where it falls in the pattern of data. So in this general trend, this outlier kind of creates the pattern. Okay? This outlier served to create the pattern, and therefore we went from having a weak correlation to a strong correlation. In this example, the pattern was already created and the outlier kind of disrupts or deviates from that pattern. Okay? In which case we would go from a strong correlation to a weak correlation. Here we go from a weak correlation to a strong correlation. So what's a researcher to do, or what's a statistician to do? There are several different diagnostic tools, and when you take advanced stats classes, you will review those, but the simplest diagnostic tool is just to look at a scatter plot of the data. And especially when there's a small number of data points, that's very possible to do, and say, do I have an outlier value? And then of course there's more complicated, well, what do you do with that person? Do you consider them a valid data point? Are they a part of the data? Do you do your calculation? These are all questions for a research methods class, and then it always comes down to, well, it depends. Do we think that this is a real score? Do we think it's representative? So some amount of professional judgment needs to be used, but the point for this introduction to statistics class is when we have a small data set, the presence of a single outlier can have a large effect on the size of the correlation coefficient, either weaken it or increase it. All right, and just going to wrap up with a couple points. When we read about associations between variables in a research paper or in a research article, it's pretty rare that you'll see a scatter plot or a scatter diagram. It's much more common that a researcher will report something called a correlation matrix. Here's what a correlation matrix looks like. It's essentially all the correlations between all of the variables in the study. And it's a matrix because we've got a table form and we've got rows and then we've got columns. Okay, so this is kind of a concise way to present all of the possible correlations among study variables in a study. So what you'll see here is we've kind of got this diagonal line that's formed, and that's using the table. We've got the first variable. This is a study I did, by the way, a long time ago now, but I was interested in whether people change their mind about different political policies when confronted with a group of people that either agree or disagree with them. Anyway, one thing that we measured was the degree to which they support whether it's okay for a government to use torture. And so that's variable one. And then going over to column, variable one is also degree of support for torture. Okay. And so the value here is just this dash, and that's common in a correlation matrix to say, well, this value would be one. It's just the correlation of a variable with itself. So that doesn't make sense. We're just going to put that dash. So then what we have in this column would be the correlation of variable one, degree of support for torture, with all the other variables in the study. Okay. Here we've got variable two, which is attitude certainty, correlation with the other variables in the study. So this is a concise way to say what are the correlations between the measured variables in the study are. Here's another example. Another thing that I didn't point out on the other table, but I will point out here, is that it is very common to designate the statistical significance of correlations using these asterisks. Okay? And you'll see that a single asterisk connotes that this correlation is statistically significant at the 0.01 level. That is, we could say even more statistically significant at 0.05, or this correlation is statistically significant at p is less than 0.01. Okay? It also says for all correlations what the number of observations is, that is the number of participants. Sometimes people skip questions and things like that. That's where you get a different number here. But again, a very concise way. Okay, so reading this table, the way to interpret this is we can say if the first variable is shame and the second is guilt, we can see that there is a correlation of 0.34 between shame and guilt. So we have a moderate positive correlation between the experience of shame and the experience of guilt, and that is statistically significant. Okay. All right, I believe that's it. Hopefully after this lecture you have it's further reinforced how to calculate a correlation coefficient, why when you calculate a correlation coefficient for a curvilinear pattern, that's likely to result in a correlation of 0 or close to it, that you have an understanding of how we determine the statistical significance of a correlation, and you could go through those steps of hypothesis testing, and that you also have an appreciation for several of the issues that are involved with interpreting a correlation, including that a correlation is not sufficient to establish causality, that there's issues that can affect the size of a correlation, such as restriction of range and outliers, and that if you were able to read a research paper and you'd see a table of correlations, you'd be able to take a look at those numbers and be able to just basically have a general sense of what's being communicated.